In this video, we're going to introduce some fundamentals of inference statistics. Inference statistics are things like confidence intervals, hypothesis testing. It's a lot of the money-making of statistics. But these inferences are based on some distribution information that we've talked about in the past. And so in this chapter, and in this section, 7.1, we're going to talk about what foundation builds that up, what distribution can build out these things like confidence intervals and hypothesis testing. So without further ado, let's dive right in. This section specifically focuses on the central limit theorem and relates to our distribution for the sample means. We have some symbols to talk about as well. To introduce the topic, we need to think about this normal distribution. That's a hint as to think about what we're talking about this section. The normal distribution is bell-shaped, has that nice curve to it, where the center, where most of your data is located, we describe the mean, or mu is the Greek character we use, of the distribution. And the spread, how wild the data is, right? How tall is that peak? How does that distribution move out? We refer to it as the standard deviation, or the Greek character sigma. Gives us the spread, how wild is our data. So one thing to notice is we have a couple different symbols here. You see how I've written mu and sigma before, but we have really two different symbols to represent kind of the same thing here. For instance, for the mean, I have this mu character and I have xbar. Why? Well, the short answer, and in fact the complete one, is the only difference is an origin story. It's where do these things come from? For parameter, for these mu characters, they come from a population. They are very significant. It represents everybody in the whole wide world when we average them together, or at least in the group that we're interested in, versus something that's kind of anecdotal, a sample, a statistic, xbar, s squared. And so we have these different symbols to represent, again, origin story, almost like a weight. How significant are they? If you have mu, if you have the population mean, okay, well, there's no need to estimate or inference onto a higher group. That is the highest population group that you can talk about. Oftentimes very difficult to get. Xbar, on the other hand, again, sample, it's anecdotal. It's okay, look, that's what we think is the general consensus. And so how do I take that anecdotal and then inference onto a larger group, onto, let's say, a population? That's where we get into confidence intervals and hypothesis testing. Again, chapter 7 is just the foundation. So we have some more symbols that I want to get to. Standard deviation is, of course, a good one that we'll talk about later. We often talk about group size. Look, how big is your group? If you're talking about a population, we use the capital N for our group size. For a statistic, we'll use lowercase n. We will use a little bit of Excel as we go forward, and so something we can look forward to using and seeing in practice. Let me slide down over here. I want to talk a little bit about the motivation as why do we need these sampling distributions and where do they come from? That's what this motivation is. If you're not interested in the motivation, you can simply skip ahead till we actually start looking at some examples. But I think the motivation is important to understand because these distributions can feel like they come out of left field, and I want us to sympathize with why we need and where these things come from. Let's dive in. So let's consider a database compiled of roughly 13 or 14,000 high school students at a Youth Risk Behavioral Surveillance System, or YRBSS for short. This data was collected in 2013. Notice the data, I have ID numbers, not names, age, I have the sex, and then I have grade, and well, maybe some of these categories are missing. And this database was built on many different schools collecting information, and so some of them may not have been as rigorous at collecting data as others. Well, there's a bunch of different categories here that we're interested in, and one of which we're going to study quite a little bit. If I look over here, this category active, this category over here, refers to the number of days physically active for 60 plus minutes in the last 7 days. And so notice this female right here was active all 7 days out of the week. That is a very active individual versus the person just above her, looks like 2 days out of the 7. So you might be asking, why do we collect this data? There's a couple reasons. I think the most cynical one is just dollar bills, right? We're trying to make money. We gather some data and then we can sell it to different schools and high school counselors and what have you. But the more altruistic one is that hopefully we can gather this information at these students who may be at risk and then track their behavior. And then over time, we can say, look, these are some good indicators, again, not causation, but good indicators that can tell us whether or not a student is at risk. And then we can offer them support before they need it. So what task are we interested with this data? Say maybe I want to estimate a value, a descriptive measure within this data. There's a couple I could estimate. For instance, if I swing out of the way here, the average height, maybe I want to look at. I can see it circled over here. These heights, I could simply add them all up, divide by how many I have. I could even, if I want to be more sophisticated, maybe more efficient, I could use the average function to compute the mean. I could even maybe a predictive feature here. I could say, look, on average, how many days per week are these students physically active? That was that active category we talked about earlier. Again, we have these 4, 2, 7, and so on and so forth. Well, there's a couple of different ways I can look at this. Say maybe we want to know the population mean for all 13,583 students, but for some reason I have very limited access. I can only access a portion of the data. I cannot access all of it. And so knowing that, is there a way that I can estimate the population mean mu if I can only get a sample? Because again, this mu comes from a population. What if I can only get a sample? Well, there might be a best guess that, look, I might not know the population information, but there should be something pretty close that, look, if we're talking about the mean and we'd like to know mu, well, ideally, it's pretty close to the sample mean. Now, how close? How do we quantify that? Well, it's certainly something we can get into. In fact, that's really what we're interested in when we talk about these sampling distributions. Let me show you what I mean. If we're talking about estimating the population mean of the number of active days these students are physically active, let's say we draw a random sample of 100 students. Again, I can't have access to all 13,583, so I only talk to 100 of them. I randomly select them, and then I calculate their average, 3.75 days. Notice that this is not going to be equal to the population, but it should be pretty close. A point estimate, it's our best guess to make this inference. Again, inference is just taking sample information and applying it onto a bigger group, maybe the population. Say maybe after some reflection, or maybe we email and we say, hey, look, can you actually tell me what the population mean information is? We hear back that the actual population is 3.9, which is pretty darn close to our sample estimation of 3.75. So the little chart here shows the statistic versus the parameter. We look at the median and the standard deviation as well, but we'll focus on the mean. One thing to notice, though, is this sample mean that we collected is completely random, right? I talk to these 100 students one day, and then I close my eyes, I shuffle it, and then I pick a random number 100. Well, I get a different group, and if I get a different group, then chances are I'd get a different sample mean. And so if I play that experiment, I talk to a different 100 students, I'm going to get a different sample mean. Let's say I get something like 3.55 days, again, different. You could imagine me iterating on this. Again, I got a first sample mean, 3.75, a second one, 3.55. I get a third, a fourth, a fifth, a sixth, a seventh, and so on and so forth. Maybe what I'm interested in is I want to know how good of an estimation 3.75 is. We can actually answer that question. I can ask questions, for instance, like, let me slide out of the way here. What is the probability that the sample mean, xbar, is less than 3.75 days? Again, anytime you hear probability, that's something we can try to write and quantify. I can write something like probability that it says xbar, so our xbar for the mean is, it says less than 3.75 equals 2. Notice at this point, there's a couple of different ways. We could try the wild, wild west of probability, figuring out, look, how big is my sample space and how many objects are there that I want. Like, it's kind of nasty, though. Instead, it's oftentimes more beneficial to ask the question, what distribution does xbar, the sample mean, follow? Because if I knew what distribution, again, say maybe it's something like binomial, well, then now I know how to find probability because that distribution has certain rules that we can follow. And maybe it's normal distribution. Well, then I can follow probability in that way. Maybe it's uniform distribution. There are others. Maybe it's exponential. Maybe it's geometric, right? There are so many distributions out there. And notice if I read the question the way it's written, probability, sample mean, it doesn't straight up tell me normal distribution. I don't know what distribution this follows. And so it's an exploration. Let's see if we can figure it out. So notice one thing we can do is we can simply look at the graph. For instance, for those 100 individuals that I talked to for that first sample mean, I could graph the data. In fact, this is what it looks like. And I see two high points, a high point here, a high point here. Modes are referred to the most frequency. This data almost looks bimodal, like it has two opposite extremes. For this representing the activity that these people are, these are people who do not go outside whatsoever. And these are like people who every single day they're outside, they're working, maybe they're in some kind of sport where that's part of their daily routine. They're always outside playing something, running something. And so we have these two extremes. Well, so let's document that here when we talk about why is this data bimodal, it seems like we have either students are not active or are very active. We have these two extremes of students. And so that's why our data is bimodal in that way. If I look at trying to fix this distribution, again, we talked about the normal distribution, but the normal distribution should be bell-shaped like this. And that is not how this single group behaves. We talked about uniform distribution that had a flat graph for uniform distribution. This doesn't seem to follow that distribution at all. Binomial distribution, if you remember, was kind of bell-shaped depending on what your p-value was. If you had a small p-value, it would go up like this, and then it would go down and be skewed to the right. It would pull a mean in that direction. It doesn't really seem to fit any of our distributions so far, but that's a perspective issue because I'm not looking at, this would refer to how X is distributed, how the students are distributed within that sample. But I'm not interested in how X is distributed, how one individual is. I'm interested in how the group, how xbar is distributed. So it's almost like we're being too myopic. We're being too zoomed in on this one group. So let me zoom out. Instead, what if I took 1,000 different samples, each sample being 100 each? And so I have 1,000 different sample means. I have x bar 1, x bar 2, all the way to x bar 1,000, 1,000 different sample means. And I took all of those averages and I graphed them on a histogram. It would look something like this. And so a natural question arises. This is a fun point of trivia. Each x bar would be different, right? They're completely random, but they would all be close to a certain number. We would think they'd all kind of tend toward a certain direction. What would you expect the sample mean to be close to? Well, I would expect that x bar is close to the population average. In fact, another way we'd write this is I would say the expected value of x bar is equal to the population mean. We saw this notation out when we were doing binomial distribution. Another way to write the expected value is the mean. But it's funny, this gets a bit distribution inside of a distribution, but we could write the mean of the sample means is equal to the population mean. We'll see this play out in a bit more detail. So when I look at this distribution, this is actually the distribution I'm interested in, not the one-time iterating one time and looking how it's distributed. Instead, I want to know how that group is distributed. When I look at this distribution, this one should look a bit more friendly. Does it look familiar, like it follows a certain distribution? Yeah, I can draw a nice bell shape on that. And so then we can say that it's normally distributed. Or maybe I should use the word approximately normally distributed. It fits roughly that bell shape. I can talk about what the average is, the mean, so that's the center of my distribution. And then I can also maybe talk about the spread. Once I have that nice bell shape, the mean and the standard deviation, I can say, hey, look, this is approximately normally distributed. And then we can do calculations on this distribution. So there's our motivation as to why these distributions are approximately normal. There's a couple more rules that we need to get into. So let's get into exactly the details here. As we've talked about, the mean is a random variable. It varies from sample to sample. You close your eyes, you pick one group. The next day you close your eyes, pick a different group. You're going to get a different mean. It is completely random. To that end, we're interested in this sampling distribution. This x bar is very near, the sample distribution is very near the overall population. But how near is it? How can we approximate or understand that nearness? Well, this is where we get into these distributions. What is the mean? Or a nice phrase, word that we like to use is expected value of the sample mean. It is exactly this. So again, this is what we wrote. Expected value of the sample mean is equal to the population mean. The way that we like to write it is over here. Distributions inside of distributions. We got a mean of the sample mean. And so that's that notation. This is the most friendly formula you'll get, well, really in any math class, but specifically a stats class. If I move completely out of the way here, you'll see it here. The sample mean normal distribution, where the mean of that distribution is the population mean itself. What do we expect to happen? That all the sample means are going to congregate around the population mean. The spread is a bit more interesting. The standard deviation of the sample means, and it's the regular population standard deviation divided by the square root of n. If you remember, n represents the size of our sample. This distribution is going to be normally distributed. We'll get into why it works out that way in a minute. But so when we look at calculating probability or future reference, norm.distribution inside of Excel is k, the value which is switching on, that's normal. We have the population mean, like normal. But notice the standard deviation is no longer just the normal standard deviation, because this is the sample mean that we're talking about. And so the standard deviation is dependent upon our random variable. And so that's the one change that we see in calculating probability. So look, this distribution is going to be approximately normally distributed, and there's two ways to know that. The first way is simply that the overall distribution, the data that you're looking at, is already normally distributed, right? You have a single distribution, and you can see, for instance, if I looked at heights on that chart, well, height is naturally normally distributed. It's not bimodal like we saw for the activity. And so this one's naturally normally distributed. The problem can say that height is normally distributed. So there's no need to go into any further theory. We have normal distribution because the data itself is normally distributed. The iterative on the sample means is not necessary. Well, let me slide over here, get out of the way. The central limit theorem, or CLT, as you'll see it referred to. This is a great and very powerful feature. If you remember the graph behind me, data is not always normally distributed. It's not nice. But as you iterate, as we take sample upon sample upon sample, things tend towards the mean. And so we get this natural behavior of sampling distribution being normal. But that's not true for every individual. In fact, if I took a sample of n equals 1, hey, it's a sample, but it's a very small sample, I will get this graph of my sample means. Because notice my sample means will just be the same thing as an individual person. And so it's important that I have a large enough sample. 1 is not enough, 2 is not enough. But we want to know what sufficiently large n will guarantee us that normal distribution. The rule is at least n greater than or equal to 30. So when you hear central limit theorem, it basically just says this, that look, if you have a large enough sample, n greater than or equal to 30, then you're guaranteed that you'll have a normal distribution. If we want to be more rigorous, we can say approximately normal distribution. And we'll talk about that approximate as we go forward. So yes, we have normal distribution, but we should understand why we have that. And it's because central limit theorem, as long as we have a large enough group. Again, if you have wonky data like we do for this example. In 2013, the number of days a high schooler is physically active for 60 plus minutes in the last 7 days is gathered from a population. The population mean, let's say, is 3.9 days, and the standard deviation is 2.564. A sample of n equals 100 is drawn from a population, and the sample mean xbar is calculated. Find the mean and standard deviation of the sample mean of xbar. This is a nice formula one for us. I can write here that the mean of the sample means is equal to, and I'll write here formula, is simply equal to the population mean itself. The most friendly formula you'll ever see in a statistics class, right up top, that should be 3.9, done and dusted. For the standard deviation, a little bit more involved, but still relatively the same. For the spread, the standard deviation, I can look right at our formula, and the formula says it's the population standard deviation divided by the square root of n. If you're wondering why I picked a nice number like 100, it's because it has a nice square root. For the population standard deviation, we can see it underlined. It's 2.564 divided by the square root of n being 100. Here we go, I can write equals. Again, you can use the calculator if you'd like to. Square root of 100 is a nice number, though. This should be 2.564 divided by 10. Divided by 10 is a friendly one. It just moves the decimal place over. So this is going to be 0.2564. I can fill that information over here. The mean of the sample means is 3.9. The standard deviation of the spread is 0.2564. Again, just because we have a mean and a standard deviation does not guarantee that we're normally distributed. And so we should ask the question, can a normal distribution approximate this sampling distribution? There's a couple things we could check. I could read the question and I could say, does it say that we're normally distributed? Because that would be one, that the question will say normal distribution. But no, it does not. So the second way, we call it the central limit theorem. Very powerful theorem. It says, look, if n is greater than or equal to 30, then you're golden. And I can look, for this case, n is equal to 100. My sample is plenty large. Yes, I can use the normal distribution. And if they ask why, you can say I have a large enough sample and just write central limit theorem or golden. I know all this distribution is going to go. I don't need a graph or building thing out. Right away, large enough sample size, I know we're normally distributed. So now we can answer that question. At the very beginning, we were talking about, look, what's the likelihood that we get a lower sample mean? If you'll remember, this was our first sample mean that we got was 3.75. The second one, sample mean that we got was 3.554. So I want to know what's the probability that I get a sample mean that was lower than the original one. That's what we can answer here. And the probability that our sample mean is less than 3.75. The beauty, now that I know I'm normal distribution, as we talked about up top, I can now start to write. Let me slide out of the way here as we write our distribution. I'll write here equals normal dot distribution. That's the Excel function we should use. And then I have 4 inputs, and I've written them conveniently, typed them up here for us for our reference. The first value is the value we're switching on. That's this. This is the K value. That should be 3.75. One done and dusted. Notice for the second one, it says the mean, but it's not the regular mean that we have up here, 3.9. It's the mean of this random variable of the mini, of the group. What is the average of the group? Well, oddly enough, the average is exactly the same as the average for the overall group. But these individual groups are the same as the overall group. Again, it's the same number, the same value, but it has a different meaning behind it. For the spread, this one is different. I can look up top. We have it. We already calculated it. It was 0.2564. And then, of course, that last input is always the same. It's always going to be 1. Once we type in those values, we're going to answer 0.2793. That's our probability. Or again, if we want to think about it in a percent, I can write that as 28%. And so when we ask the question, look, my first sample mean was 3.75, and I want to know what's the likelihood that I'm going to go under that? Man, I'd be pretty low. It looks unlikely. And look, I in fact did get that. I got 3.55. This notion of probability is actually the birthing place of hypothesis testing. When we're talking about the closeness, that's where we get into confidence intervals. And so again, this distribution, these normal distributions, is what builds those inference-based statistics, which is where a lot of the money is in the actual practice or the use of statistics. In this example, I want to highlight the difference between one person and many and what they tend towards. According to the Center for Disease Control and Prevention, the CDC, for persons 18 of age and older in the United States from 2012 to 2015, the mean total cholesterol level was 197 milligrams per deciliter for mg/dl. Use the standard deviation of 35 mg/dl and assume that the cholesterol levels for the population are normally distributed. Anytime that distribution is highlighted, it's important to circle, highlight it, make it as obvious as possible. That way, going through when we're asked things like probability, percentiles, maybe what is the mean and standard deviation, we have our frame of reference. We have the function or the world we're living in this case, normal distribution. Let's dive in. What is the probability that a randomly selected adult from the population will have a total cholesterol level less than 183 milligrams per deciliter? Here's a little hint. What is the mean and standard deviation? So they're asking us probability. I can start right away. This graph is actually related, but I'll get into it in a minute. It says probability of, notice it says an adult. It's not talking about a group. I don't see it say sample mean anywhere. So it's regular probability that one person has a cholesterol level less than 183. Once we have our probability less than, we can go right into our distribution. I'll type it up here. It should be equals normal dot distribution. Those 4 inputs for us are K, we need a mean, a standard deviation, and 1. K is the value we're switching on. Fortunately, we have our probability written appropriately. It should be 183. The mean, notice it's the mean of X. How is X distributed? Well, that's a regular mean. I can go up top and see it says the mean total cholesterol level is 197. So I'll write 197 for the mean. Then it says the standard deviation. Here we go. Standard deviation is 35. And of course, that last input is always a 1. And so I get my probability here, no problem. In fact, the probability it says is 0.3446. Or if I want to think about that as a percentage, I can write 34%. And that's for one individual. And that's really what this graph shows. Again, for probability, for these continuous distributions, area is the same thing as probability. And this represents 0.34 or 34% of my data. That was for one person. Notice my mean, my average is 197. And again, that's deviating from the norm. It's away from the norm. And still a good chance that if you walk into somebody randomly and you say, hey, look, cholesterol levels, blah, blah, here's the mean. It's likely. What if we take a group of people? How will that change? What is the probability that a random selected sample of 49 adults from the population will have a sample mean, there's that key word, cholesterol level less than 183. So very similar question from above, but in this case, I'm asking, and I'll write it here, the probability that the sample mean, x bar, is less than 183. Again, here, my random variable is many, not just one person. I got n equals to 49. I'm asking these people deviating away from the mean. The graph gives you a little hint. We're not going to get very much probability, but let's see why it works out that way. And once I have less than, I can go right into my distribution. And when we're asking what distribution this follows, it says normal. We don't need to check the central limit theorem because the original distribution is normal. The iterative one, the sample mean, is also normal. Let me write here equals normal dot distribution. And I have my 4 inputs. The first one is the same as before, 183, no difference there. As we go forward, though, we're looking at the mean and the standard deviation. But notice here, this is not just the regular old mean, the mean that we're used to seeing. This is the mean of the sample means, x bar. Now, fortunately for us, we can go look at a formula. This one's actually the most friendly formula they'll get. It's the exact same thing, 197. But what I want you to appreciate is it's the same number, but a different character. For the next one, this one is actually going to be different. It's the standard deviation, but it's the standard deviation of the sample means. You can look at the formula. It's the population standard deviation, which in this case is 35, divided by the square root of n. In this case, it's 49. Again, maybe you can appreciate why I have nice square root numbers there. It makes the numbers work out a bit more friendly for us. So that'll be 35 divided by the square root of 49 is 7. 35 divided by 7, 5. That 5 is the spread here. And then, of course, that last input is always the same. It's always 1. So if I type in those values, I actually get a very, very small probability, 0.0026. As a percentage, that's 0.3%, not 34, 0.3. If I slide out of the way here, maybe we can see it a bit better on my graph. I'll write here, 0.0026. Let me zoom in so we can kind of compare these two. When I talked about one person, what's the likelihood that one person deviated from the mean? Well, it's pretty likely, 34% chance that you would run into somebody that deviated from the mean that was away. Likely. The same value though, but instead of one person, I take 49 people and I say, hey, look, with these 49 people, what's likely that they all, on average, deviate from the mean? Notice the same movement, 183, it is a dramatic difference in probability. That all these people deviate, very unlikely. And in that sample, you might have one person that deviates, but on the whole, you're gonna have some people who have less cholesterol, some people have more, some people have an average. And if you take all those individuals, the sample deviating that far away from the population, unlikely, don't count on it. And there's often that adage that goes, one person is wild, who knows what they're gonna do. But as you look at a group of individuals, they tend towards the mean. They seem to be a bit more predictable. We can observe that in our probability, but we might be saying, where does that come from? Well, if you look over here at the spread, again, this spread describes, it's a measure to tell you how wild your data is. One person, 35 units of cholesterol can go either way, who knows? But as you get 49 people, a huge group, well, look at that spread. The spread is 5, much smaller than before, much more predictable because they tend toward the mean in a much tighter fashion. And so we're often interested in saying, okay, look, that was only a sample of 49 people. What if I took a larger sample? What's going to happen to my probability? In fact, that's this next question below. Would the probability in part B be larger or smaller if the sample of 100 adults were polled? To answer this question, we can look at the spread that we've talked about before. Again, the spread is always population standard deviation divided by n. And so I can look at, if I had 100 people, let's say, my standard deviation would be the same at 35, divided by the square root of now, instead of 49, I'm talking about 100 individuals. This would be 35 divided by 10, or 3.5. So notice, that would be everybody who should be closer to the mean. I have less spread. Because again, more people means they tend more towards the mean. And so you can observe a trend here that when I was talking to one person, there was a lot of probability, 0.344. As I talk to more people, less probability, very unlikely. And so if I talk to even more people, I'm going to get an even smaller probability. Let me slide it out of the way so I can circle it appropriately. Here it is. Smaller. Because again, they tend more towards the mean. The likelihood that they're going to be way out at 183 or less, unlikely, And that's certainly the trend that we can observe. So to clean this one up, again, the math, maybe not that difficult. It's just probability for normal distribution. We've seen those in the past. But the thing I want to highlight for you is that adage that one person is wild, who knows what that person's going to do. But as you get people in groups, they tend towards the mean. They tend to be a bit more predictable because you have some people who are lower, some people who are higher, and they tend to average towards the mean. And that's certainly what this example highlights. Let's continue that conversation and speak about parameters. Maybe we're really interested in estimating a parameter like the population mean, mu. Would you rather use a small sample where we're thinking, look, this is cheap, it's easy to gather, or would I rather talk to a large sample where I'm having to spend more money because either I'm having to pay somebody to go out there and ask questions, say, look, how do you feel about X? Which one would I prefer to use? Well, if your goal is to solely estimate a population mean, mu, how am I estimating that? Well, as we've talked about, we're going to estimate it with our best guess. We called it a point estimate, is xbar. And so the question in this small or large sample is, look, how good of a point estimate of a guess do we want? Well, the short answer is the larger, the better, right? The more people I talk to, the better. You could imagine if I only talk to 100 people when my population is, let's say, 10 million, well, maybe that sample is pretty insignificant. If I can add a couple more zeros onto there, well, now this is a more significant group, 10,000. Maybe that's a good sample. But in fact, if I had a sample that was the exact same, maybe 10 million, well, that's not a sample anymore. Now this is a perfect estimation. So the rule of thumb is, look, larger is always better. The more people you talk to, the better point estimates you're going to have, the better guess, the better approximation you'll have for population information. The only limitation is oftentimes money. It's hard to talk to everybody, but also convenience. It's very difficult to get everybody's information. And that's why census information oftentimes is incomplete. It's very difficult to get all information from everyone. Next example, you're researching a startup game targeted at 35-year-old demographic. Your idea is to develop a strategy game that can be played by men in their late 20s through their late 30s. And so this is what you're trying to build this game around. You're trying to figure out what they're interested in, kind of market your game in that way. Based on an article's data, industry research shows that the average strategy player is 28 years old with a standard deviation of 4.8 years. You take a sample of 100 randomly selected gamers. If your target market is 29 to 35-year-olds, let's say, should you continue with your development strategy? We can actually quantify these things. We can quantify how likely it is that people will play. Again, we use this word random sample, but that's often who's going to play your game. And it's your job as a developer to try to build a game, to develop something that's attractive to as many people as possible. And that's exactly what we can quantify here. Find the probability that the sample mean xbar of ages is within 29 to 35 years old. And I can write this, they say probability, I can write the probability xbar, so we're talking sample mean, but notice we're looking at between 29 and 35. So let me write 29 on one side, less than or equal to xbar, less than or equal to 35. Again, you might be asking the pedantic question, shouldn't this be strictly less than? And strictly less than? Well, yes, but in these continuous distributions and normal distribution, it can go either way, is equal to. As a little side note, whenever we're doing probability, you should be asking yourself, what distribution does this follow? Well, the nice part of it is if I see n is greater than or equal to 30, I know by the central limit theorem, this thing is going to be normal distribution. And so right away, now we know how to compute probability. I can even do things like percentiles as well. Unfortunately, though, the way this is written between does not fit with normal distribution, at least not with our Excel function. And so everything has to be less than. As we've shown in the past, luckily right here, this is exactly the form we need. Let me write it as the probability that xbar is less than or equal to 35. And then we're like, hey, look, we're golden. But not quite, because it's missing something. I still have xbar is greater than 29. Whenever you hear greater than, we usually do 1 minus to compensate. That's what this minus will say. It will say take out the probability that xbar is less than or equal to 29. And now we took something that said between, which we cannot compute the probability of, to two probabilities that we can. So in this blank below, I'll write out exactly how you can calculate this probability in one cell. Here we go. Let me write equals. For normal distribution, mostly for convenience sake, let me abbreviate n.d. But in reality, if you're typing this out, you should write normal phat distribution. We require 4 inputs. We require k, the value we're switching on. For this first one in blue, that's 35. I then need a mean, but it's this mean of the sample means. Fortunately for us, if we can look at the formula, it's the exact same thing. We should be writing 28. The standard deviation's a bit more tricky. Let me do the calculation over here. The standard deviation of the sample means is the regular population standard deviation, which we can look from the question is 4.8, divided by the square root of n, which in this case is 100. You can either type this whole thing into your calculator. 4.8 divided by the square root of 100 is divided by 10. And so it should be 0.48 for our standard deviation. So I'll type that right here, 0.48 for our spread. And of course, that last input is always the same. It's always going to be a 1. And that's the probability that x bar is less than or equal to 35. Let me switch over to green to do my other probability that x bar is less than or equal to 29. I'll write normal distribution for the same reason as the first one is normal. Parentheses, what's the value we're switching on? 29. The mean and the standard deviation are the exact same as before because it's the same x bar. We should write 28 for the mean and 0.48 for the standard deviation. The spread, exactly the same. And then our last input, of course, is 1. And so when we ask the question, look, what's the likelihood that I'm going to get a sample of 100 individuals playing my game and their average age is going to be 29 to 35, somewhere between there? I'm going to go for unlikely. The probability is 0.0186. Or as a percentage, I can round that. And let's say there's a 2% chance that the random people who are playing my game are in between this age range, which suggests that maybe there's something wrong with my marketing, or at least the way that we're building out this game. Because the likelihood that people playing my game are inside of this age range, or at least their average age is in between this range, is terrible, right? It's 2%, not going to happen. And so then maybe it's up to us, do some self-reflection to say, look, it's unlikely that our gamers are going to be this age. In fact, the layman maybe could notice, look at this average over here, 28 years old. For some reason, strategy game players seem to be younger than our category. We're outside of the mean. In fact, the likelihood that we're going to have this many gamers, unlikely, don't count on it. And so we can ask this question, are there many strategy players within your demographic, 29 to 35? Well, it's impossible to say exactly how many, but certainly when we're interested in developing a game, we have the average age of 28 and we're marketing to 29 to 35-year-olds, I'm thinking this is not likely. No, there's not too many people that we can really market to. Again, the probability that x bar is inside of this interval from 29 to 35 when n was 100, don't count on it. There is not many. There is a 2% chance. And so why are we making this game designed to target these individuals when the fact of the matter is these people don't play this game? Maybe we could change that. We could buck the system, but oftentimes this is the safe method that we like to play towards. What demographics out there? How can we reach them to play our specific game? Time to go back to the drawing board with this one. Next example. The mean number of minutes for app engagement by a tablet user is 8.2 minutes. They seem to, for some reason, drop interest after that time. Suppose that the standard deviation is 1 minute. And I would take a sample, let's say, of 60 tablet users. Let's see if we can answer some questions. What is the standard error, SE, of the sample mean? Again, to understand sample mean, we can simply write x bar. When we refer to standard error, we can think about that like wiggle room, like how off are we? What is the spread? How wild is our data? Here's a nice formula for you. SE, for the standard error, is equal just to the spread, or we quantify that as the standard deviation. But not just any standard deviation. This is a standard deviation of the sample means. So here's our formula. It's the regular standard deviation divided by the square root of n. We can look up top. The standard deviation is 1 divided by the square root of n. In this case, I talked to 60 tablet users here. This one may be less friendly to compute by hand, but we can simply whip out a calculator. 1 divided by the square root of 60. We should get 0.1291. This is the standard error. How wild is this data? But how can we use that spread? Let's say you design an app that will pop up an ad after a certain time. Find the 30th percentile from the sample mean time for app engagement for a tablet user. There's a line in the sand, we call it 30th percentile. Look, 30% of users are going to drop off before this point. And there are 70% of users that'll stay beyond that point. Again, for app engagement, they're looking at this app, and it looks like on average, after 8.2 minutes, they're like, okay, I'm done with this, I'm doing something else. And so I'm like, look, maybe the 30 percentile is pretty safe for me, that if I do pop up an ad, I'll have 70% of people that will see that ad. And so with the 30th percentile, I have 70% of people who will stay, who are on that app. They're not going to swipe away. They're looking, and then, an ad pops up and it'll catch them. Versus 30% of people will leave. They'll leave my app early and they're not going to find the ad, and then I won't make easy ad revenue. And so that 30 percentile we consider to be safe. That's a good mile marker where, I'll lose 30% of my ad revenue that I could make, but I still capture 70% of my audience. And so how do I calculate percentiles? There's a couple different ways. It depends on the distribution you're dealing with. For this one, I'm looking, it doesn't say anywhere normal distribution, but I do see that we have a mean and a standard deviation. Is it normally distributed? There's a couple different ways we can answer that question. Again, the first way is if the question literally says normal. And the second way is the central limit theorem. Beautiful theorem. It just says, look, is your sample greater than or equal than 30? Certainly, I can view my sample. It said we talked to 60 tablet users. Yes, we're good here. This does satisfy. This is normally distributed. And so inside of percentiles, we actually have a function for normal distribution, and it looks like this. In fact, I have a little hint up here for our reference. I can write it like this. Norm dot inverse. Again, anytime you hear percentiles, think inverse. And I have 3 inputs to put in. The first one is just P, it's the probability. In this case, that should be 0.3 for 30 percentile. The next 2 inputs, don't be tricked, are not the regular mean and standard deviation we see up top. Instead, this is asking for the sample mean time. This is asking for the 30th percentile of xbar. So this is not just the regular mean, this is the mean of the means. For us, very nice formula, 8.2. For the standard deviation, it's not the regular standard deviation, it's the standard deviation of the sample means, which we did up top is the sampling error or the standard error. That's going to be 0.1291. And after a little bit of work in Excel, we should get 8.13 minutes. And again, the whole beauty of percentiles, or the whole reason we're interested in them, is because it gives us a nice line in the sand to say, look, if we're going to make pop-up ads, and I want to make sure to capture a good amount of audience, I don't want to just put an ad at the average. Because again, with normal distribution, the average, the mean, is smack dab in the middle. It's the median. And so if I want to capture a bit more individuals, let me pull back that time, give an ad a bit sooner. 8.13 is a good mile marker, at least for us, to say that that's going to capture a good amount of our audience with a sample of individuals who are using our app on a tablet. What about some probability? Find the probability that the sample mean is more than 8.5 minutes. And here we have probability, so I'll write right away, probability, the sample mean. So again, this isn't just one person. We're talking about xbar is more than, so I'll write greater than 8.5 minutes. What's the probability that our average is that people are going to spend more than 8.5 minutes on our app? The problem with more than is, again, anytime we see more than, we can't do it directly. Instead, what I have to do is I have to convert it. And whenever you see greater than, we should always write 1 minus and do the less than. So I'll write it right here. I'll write 1 minus for probability. It's the normal distribution. So I'll write normal dot distribution. That's what you should type in if we're trying to find the probability. And I have 4 different inputs. I have K, that's going to be 8.5, the time that we're switching on. Then I have the mean and the standard deviation. That should be 8.2 for the mean, 0.1291 for the standard deviation. And of course, with normal distribution, the last input should always be 1. And it looks like, what's the probability that we're going to get over the norm? 8.2 minutes is the norm. It looks like the probability is unlikely. That's 0.0101. That's, if we want to convert it into a percent, that's a 1% chance. And so if we're developing this app, we launch it out, we have these ads, and we look at our engagement, and our engagement is quite a bit better. Maybe our actual engagement from our sample, and it's something like 8.7. It's pretty good engagement. And I say, what's the probability that I'm that far above the mean? 8.5 minutes, let's say. And we say, oh my gosh, can't believe it. There's very unlikely that this is the case. Well, then it might not be a coincidence. We might be an anomaly. This average tablet user may not be who we're attracting. Maybe we either have an amazing app that is not just normal, is not average, but above average. And we can actually quantify that. We can make a claim as to say we are very above average, above normal. There's a 1% chance that we got this audience. And this is the argument that you often get with hypothesis testing, that we say, look, I think that number's wrong. I think we, in fact, have a special sauce. I think we're different. I think our average is above that population average. And in fact, we can quantify these things as probabilities. All these sampling distributions, let me recap and wrap with this. All these probabilities that we compute, they serve a purpose, not just in, hey, a blank probability, but they lead ways into hypothesis testing. In fact, quite directly here, it's exactly what we're doing here, but also with confidence intervals as well, which answer a question to say, I have this sample mean of 8.7. How close is that to some mystery mean that I don't know? That's what confidence intervals do. They say, look, I can tell you about how close that population would be, say maybe if we had no idea. And so it's really what we're exploring here. We're understanding confidence intervals and hypothesis testing, but we're building that foundation so that when we do these bigger calculations, when we do these bigger inferences, we understand where the math and where these calculations come from. If you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.